Dear coders, thank you for viewing our presentation. We are with University of Guanajuato, Mexico and Jiangnan University, China. This presentation is on algorithm designs for tracking moving objects with colored process noise. Here is the line of our presentation. Introduction. Here we present a problem which is related to reduce errors while tracking a moving object trajectory with a colored speed noise. The Kalman and unbiased finite impulse response filtering algorithms are modified assuming the Gauss-Markov noise nature. In a state space model with colored process noise includes the Kalman and UFIR filter algorithms modified using state differencing. In tracking of a walking human, we present the estimation for the position of a person using as a vector measurement a set of GPS data. Conclusions. We discuss the results of the proposed algorithms method against classical estimators. In tracking moving objects in speech processing, the process noise becomes colored when a control mechanism is ignored and not included in the state equation. As example is the human speed, which was shown to be colored in many investigations. A state estimator should thus be used such that its algorithm is modified for colored process noise. There are three approaches on how to induce colorless to the estimation algorithm: the state augmentation, the measurement differencing, or by the Petevelo algorithm. For colored process noise, state augmentation does not make the Kalman filter ill-conditioned. Therefore, this approach is considered as a standard solution. Measurement and state differencing hence still attract the attention of the researchers. In Kalman filtering, the problem with colored and time-correlated noise is solved by either rederiving the Kalman gain or decorrelating noise vectors. In this work, we are focused on the moving object state estimation with colored speed noise. Therefore, we first introduce the Kalman and UFIR filter modifications for the colored process noise using state differencing and then apply the algorithms to the global positioning system measurements of walking humans assuming a colored speed noise. A moving object can be modeled in discrete time-state space, where the first value in the vector state is the distance, the second is the velocity, the third is the acceleration, and so on. If the measurement is also linear and the object noise is colored, one may assume that the colored process noise is Gauss-Markov and represent an object with the following state and observation equations, where x is the state vectors, y is the measurement vector, H is the observation matrix, W is a colored Gauss-Markov noise, matrices A, B, and theta are square and non-singular, and the matrix theta is such that the colored noise W is stationary. It is supposed that noise vectors mu and V are white Gaussian, zero mean, with covariance Q and R, and they are uncorrelated. Modification for colored process noise using state differencing. Similarly to measurement differencing and aimed at avoiding colored noise W in X, the space state model can be modified to obtain the following form, where G is a new state and zeta is a new observation. The matrix pi is specified in this way, and theta hat is a weighted matrix where f are calculated by these recursions. Therefore, the initial value f sub 0 is a critical issue. Let me consider this point in more detail. f0 can be specified if we think that the process before the initial point at 0 time invariant and transformed to the non-symmetric algebraic Riccati equation. The problem is that this equation is generally not unique. So we introduce g sub 0 as a reasonable initial state to run. Kalman filter algorithm for colored process noise. There are no special comments on how to modify the Kalman filter algorithm for colored process noise. If the matrix F is previously defined via the recursive equations, a pseudocode for a relevant Kalman filter algorithm is listed in the figure. It can be easily observed that by theta equal to 0 and f equal to a, the algorithm becomes the standard Kalman filter and therefore can be universally applied for process with and without Gauss-Markov colored noise. Another option to provide state estimation based on model is to use the UFIR filter, which does not require any information about zero mean noise and is more robust than the Kalman filter. The UFIR filter provides a state estimation over an averaging horizon of endpoints to produce a near optimal estimate. These filters require an optimal averaging horizon to minimize the mean square error. A pseudocode for the UFIR algorithm for color process noise is described in the figure. Simulation example of moving object tracking. Concerted of tracking for moving objects, we now simulate a process with a tracking state equation to investigate state estimation errors produced by the Kalman filter, colored Kalman filter, UFIR filter, and colored UFIR filter. We consider a two-state model described by the next set of equations, where tau is equal to 1 and the white Gaussian noise had the standard deviation of 0.8 and 1. The most critical question now is how the modified algorithms improve performance. We therefore compute the root median square errors produced by all filters and sketch the results as a function of the color factor theta. What follows from this simulation can be summarized in this way. Under the ideal conditions, when the model and noise are completely known, the Kalman filter and colored Kalman filter perform more accurately than the UFIR filter and colored UFIR filter. The modified colored Kalman filter and colored UFIR filter both improve performance. However, the improvement appears to be essential only when theta is greater than 0.5. Otherwise, the colored Kalman filter and colored UFIR filter may not demonstrate efficiency. When theta approached unity associated with the Gauss-Markov noise stationary, the colored Kalman filter and colored UFIR filter perform much better than the Kalman filter and UFIR filter. That means that the filters modified for Gauss-Markov colored process noise are efficient when the process noise is highly colored. Tracking of a walking human. We now consider several walking human trajectories measured each second using GPS loggers and phones. data are available from a dataset. Our goal is to estimate the walking human speed using the standard Kalman filter, UFIR filter, the colored UFIR filter, and colored Kalman filter modified for colored process noise. We suppose that human speed noise is colored. Under such a supposition, we consider a tracking problem along the coordinate x, employing the same model as in simulations. Because the ground truth is not available in our experiment, we will analyze the results by comparing the filter outputs. Measurement data does not contain sufficient information about the process and noise. We therefore refer to the average human speed of 1.4 meters per second and assign a standard deviation of 0.8 meters per second. We also notice that the GPS standard position and service is available with errors less than 15 meters with a probability of 95% in the 2 sigma sense and a substandard deviation of 3.55 meters. Although these values are not exact for the model and measurement, they affect all filtering algorithms equivalently that allows comparing errors. Estimates provided by all filters are also shown here, and that allows make the following conclusions. It is neatly seen in the figure A that noise in both experiments is definitely not white. This confirms that the human speed noise is colored, although its coloredness is a topic for special investigations. The Kalman and UFIR filter produce consistent estimates, although the UFIR filter generates a bit larger excursions. The colored Kalman filter and colored UFIR filter estimates also appear to be consistent, although with a bit smaller colored process noise waves at the outputs. Conclusions. Estimates of the walking human speed provided by the colored Kalman filter and colored UFIR filter modified for Markov-Gauss colored process noise have shown a better performance of the estimation algorithms, especially when the speed noise color factor is large. The results were achieved by applying the state differencing for the square and non-singular system matrix, process noise matrix, and noise color matrix that allow providing an accurate state estimation while solving the nonlinear algebraic Riccati equation to specify the modified system matrix. Extensive investigation of GPS-based data have confirmed the efficiency of the modified algorithms. Thank you for your kind attention.